In this video, we are going to finish our 8-bit CPU project. Hey guys, welcome back to the channel. So in the last video, we finished our control unit. In this video, we are going to put all the components together and assemble our final CPU, and we will probably finish this project in this video. So if you haven't watched my previous videos yet, I would suggest you to go back and watch all the videos first and then continue watching this video. If you haven't subscribed to the channel yet, please subscribe and help me reach my 1000 subscriber goal. So without wasting any time, let's get started. As you can see, I have changed my setup again, and now we are using Quartus Prime Lite. That is because recently for a seminar I got this FPGA board which is Intel based, and I will be implementing the CPU on that board. That's why I was changed my setup to Quartus. So check it out on the internet. It's really simple. I'm not going to use any specific features of Intel board, so that shouldn't matter to you. You can use any board you need to implement this CPU. So I've made this CPU.vsd file. Let's make our entity. Our CPU entity will have 3 inputs: clock, reset, and 1 output port. So we will connect this output port to few LEDs which are present on MAX1000 board, and they will show us whatever we put on our output port of our CPU. So it will be standard logic vector. So one by one we will go to every component and copy the entity and change it, like declare a component. So this is for program counter, and similarly we will do it for every component that we have made from the first tutorial. So now we will make instance of each of this component, and we will then declare some few signals to connect everything together. So let's make those instance first. I'll just copy this port from here. So here we have made the instance of each of the component. So let's start with connecting the signals. So we have to we can connect clock and reset as is to each of these components. Just one thing, the way our halt instruction works in this CPU is by halting by asserting a halt signal. So we will just create a clock signal. We'll create a clock signal like this. So when the halt signal is asserted, the clock will be stopped, and we will feed this clock signal to each of our components. So let's declare this clock signal first and then halt signal. So signal standard logic. Halt signal will be standard logic as well. So let's assign this clock signal to every clock. I mean every component. Now we will connect reset as is to every signal, I mean every component. So let's connect the resets. Okay, now we will connect the rest of the signals to our components. So program counter has three control signals: program counter enable, program counter output enable, and program counter load signal. So we will declare three control signals for that, and we will connect those to our program counter. These control signals will be driven by our control unit, so we will make those connections later. So let's make these signals. Let's declare these signals here. Lowest 4 bits of our main bus will be connected to input as well as output of the program counter. So let's first declare our main bus signal. Main bus will be standard logic vector of width 8. And we will connect only lowest least significant 4 bits, so that is 3 down to 0, to both input and output. For our control unit, it will take instruction in, and as we saw in we built 16 bits of output, or 17, I don't okay, it's 17 bits of output. So that will be our control unit output signal, and it will take instruction which is outputted by instruction register, which is declared somewhere here. Yeah, this is the instruction registers. Its output will be connected to control unit's input. So we'll declare that signal. So this is our instruction out signal declaration. Our instructions are 4-bit wide, so control unit out signal we will declare. So that is 17 bytes, 17 bits. So we'll connect it here, and we'll connect this to output of our control unit. Next is memory address register, this one. So it takes one control signal and input and output. So here we will have memory address register load signal. We need to declare this. Input to memory address register would be lower 4 bits from our main bus. And memory address register's output will be directly connected to our RAM's address input. So we will declare a signal. We'll call it memory address register to memory signal. This will be again 4 bits. So 3 down to 0. So our memory will have 2 control signals, which are, we will call them memory load enable or memory write enable, you can call whatever. And memory output enable. For consistency, let's just call load signal. We'll need to declare these two. Data into memory will be main bus, and data output as will be on main bus. As we saw, we'll just copy this output from memory address register and put it as address input to our memory. Okay, next is our instruction register. So it has two control signals, load and output enable, and it has two data signals like input. It has one output. First let's connect these control signals. We'll call this instruction load signal and instruction register output enable signal. Let's declare these. Now input to this memory instruction register would be our main bus, and we will connect the output to a separate signal, and it will be connected to one part of it will be connected to our main bus, and one half will be connected to instruction out signal, which will in turn go to our control unit. So let's just declare this signal, instruction out signal. This is 8-bit wide. So upper 4 bits of our instruction out signal will be connected to our instruction out signal, which is connected to our control unit. And then when instruction output is enabled for instruction register, we will connect the lower 4 bits, we will put the lower 4 bits onto our memory address register, main bus, sorry. So main bus 3 down to 0 will be connected to this lower 4 bits of our instruction register output. When our instruction output enable signal is 1, otherwise it will be put to high impedance state. So okay, next is our A resistor and B resistor. So again, these have two control signals each, so we will first need to connect those. Resistor A, we'll call it output enable. Similarly for B resistor, and for our output register as well. As I mentioned earlier, our output resistor will be connected to LEDs on that MAX1000 board. So let's just quickly declare these control signals. Now we will connect input and output to our resistors. So it will be to main bus. For both the resistors. Output ALU is our special port which connects our resistors directly to our ALU. So we will make new signals and connect those. Let's declare these signals. Now our input of our output resistor will be connected to main bus as well. Its output we will leave open and we can connect this output directly to our OP signal, which is this one. So for ALU we have two control signals. Let's declare those. ALU enable signal and ALU output enable signal. So resistor A in will come from resistor ALU signal. Similarly for B resistor. Currently we are not using carry and zero outputs, so we can leave them open and result out will be put on main bus. One more thing we have to do is connect all the output from our control unit, which is here, to respective control signals. So I'll do that. Now if we go to our control unit, here I have written what is the sequence of our control signals is. So according to that, I will connect my I will connect the control unit output and all the control signals we have connected. I have put the control signals. I have connected all the control signals to control unit output. Make sure you get this sequence right according to whatever you have put in your control unit. In my control unit I have this sequence, so I have connected accordingly. I have compiled this design off camera. Like I had to stop the recording because my laptop cannot handle both recording and compilation at the same time. So one little modification, additional thing I have done is I have this top module where we make an object of our CPU and one counter. So I have used this counter from inbuilt IP of Intel. So this counter is for dividing our clock frequency. So the MAX1000 board I have got runs at 12 megahertz. If we run our code at that speed, we won't be able to see output. That's why I'm scaling it down, so dividing the frequency basically. So that's what I have done here. When I put this code in GitHub, I will put my own counter unit there, so that you don't have to be dependent on this Intel IP. So there is one more bug in our previous code in ALU. So ALU, there is this OP, if we see the operation opcode, so I had written 1 for addition and 0 for a subtraction in earlier code, but in my control unit I had treated 0 as addition and 1 as subtraction. So I have corrected this here. You can use any of the opcode for any of the operation. You'll just have to modify your control unit according to that. So I will put this updated code on GitHub as well. So coming to memory, I have commented this initialization function which we used in our simulation. I have hard-coded a program. This is basically a counter program, so which counts from 0 to 255, that is FF in hexadecimal. And yeah, so I will put on the screen what is the assembly instructions for this code, and I have converted those to a hex by hand and then put this here. So this is hard coded. I have compiled this, and now I will flash this on our MAX1000 FPGA board. So I have connected my FPGA board and I will flash this code. So it is successfully flashed now. So here you can see the binary counter in action. Since our clock, we have divided our clock, it is we are able to see the counts. So that's it for this video, guys. Thank you for watching the video. Let me know your thoughts in the comments below. If you haven't subscribed to the channel yet, please subscribe and help me reach my 1000 subscriber goal. See you in the next video.